So this is Beyond Horizons TMUA paper number 2 that's been written by them. I'll put the link for them for their website in the description down below along with this paper. They have written more papers which you can purchase from their website, and they also of course do tutoring which you can also speak to them about. So I'd recommend you think about doing both those things. But for now we'll just do this paper and leave it there. I should say before we start though, I don't have a mark scheme for this paper. I haven't looked at it. So this is going to be an interesting one in terms of I'm actually not sure whether the answers to these are right. It's more just my feelings, and this is kind of how I would actually have gone about doing an actual TMUA paper, because of course when you do a real paper you don't know whether your answers are right or not. You don't get to check. So a lot of this is going to be on vibes and on, well, I sort of thought this was the right answer, and it turns out it was. And even if there's a mistake, I'm sure mistakes can be spotted in the comments, and people can point them out. Anyway, we start by solving this inequality, which involves sketching a graph, right? We can factorize x squared minus 1 into this, and then we can just put 3 roots down at minus 1, 1, and 2. So the graph must look like this because it's a positive cubic. And we're asking when it's bigger than 0, so it's in between those two roots and beyond that one. So in between 1 and minus 1 and beyond 2. And that'll be option E. And the first question is, I think, easily done. Second question, we can cheese. If M can do it in D days, then that means that if we're being asked for how long it takes them if there are M plus R people, well, if R was 0, it should still take D days. So we can just look at these options here and say, well, if R is 0, which ones are still D? And the only ones are A and C. So, okay, that just leaves A and D. That just leaves A and D to sort out. And we can next think, well, if you're getting more people to do this, if you're including more people, more R, then that means the amount of time it should take should be lower. And A increases, right? It's saying it takes D plus R, which can't be right. It can't take more days for more workers. So therefore, the only logical one is D, and we can just cheese that question quite hard. The next one, we have 4 committees, and we have a bunch of members. So let's say member A, they have to be part of 2 committees. So what I'm going to say is I'm going to start with 4 members, A, B, C, D, and just put them like this. But they have to be part of 2 committees each. Let's just slide each one along a bit and do this. So A, B, C, and then D back here. Now this nearly works, except this committee here doesn't share a member with this committee, and likewise this one doesn't share one with this committee. So I think we need to insert another member into the first and third group. We'll call that the F member, and the second and fourth we'll call the E member. And now they all share one person, and everyone is part of 2 committees. So we've met both conditions. So either the answer is B or D, and this is one of those times where, you know, I'm sort of just going to go ahead and say that I think the answer is B. It might even be lower than that. There might be a configuration for 4 that works, although I don't think there is. I can't see how that works with what I had before. But I don't think we can have more than this, because the moment we put any person in any other 2 committees, that means those 2 committees will share more than one person all of a sudden. And so I'm just going to go ahead and say, again, I can't spend 10 minutes on each question. That's not how TMUA works. I'm just going to go ahead and say the answer is B. Because I found it, and I don't think initially it just seems that I'd be breaking the rules the moment I go any higher than that. So we'll just go with that and move on. A person X shakes hands with person Y, then of course Y shakes hands with X. In other words, every time you do a handshake, if you're adding up the total number of handshakes done, you have 2 handshakes per handshake, right? Because X has done 1 and Y has done 1, so that's 2 handshakes in total. And that's kind of the logic that I'm going to go for this question. So with 99 people, one of these following statements is apparently true. There is at least one person who shakes hands with with exactly an odd number of persons. Well, what if no one shook hands with anyone? Like they just all entered the room and fist bumped instead, or just awkwardly ignored each other's existences, right? This would mean that everyone's handshake number would be 0, and 0 is apparently an even number, which it totally is. There's nothing controversial about that at all. 0 is totally even. This also, I think, gets rid of C, because C says there's an even number of people who shake hands with an even number of people. Well, if no one shakes hands, then that means there are 99 people who shake hands with 0 people. So I think we can also get rid of C from that. And then we just think about B. There's at least one person who shakes hands with exactly an even number of people. Well, to do this, I kind of thought, well, if we say X1 is the number of handshakes done by person 1, then, like I said right at the very top, the total number of handshakes done is even, because every time you do a handshake, that makes maybe, person 1 shakes person 3 hand. That puts an increase of 1 on the 1 person's count and the 3 person count. You increase these by 2s. So the sum is definitely an even number. So therefore, well, how do we get 99 things to add up to make an even number? Well, if you made the first 2 odd, they would add up to make an even together, and then you could make the next 2 odd and the next 2 odd, and so on and on and on. But you've still got this 99th person who's on their own, and they would have to be even to make it totally even. Or you of course have evens earlier, but then of course you've got at least one person who's done an even. So I think in either case you're going to have to end up with at least one even person here to make this sum work. So that was what I said. Because instead of this sequence, then AK is composite, so it's not prime if these things here. So okay, we've got this sequence of numbers, and the key thing here is the alternating digit sum rule for 11s. That's the key idea here, I think, because basically this number here, when we do the alternating digit sum, that's 1 minus 0 plus 1 minus 0 plus 1 in these cases. And what you notice is that you're always taking away 0 and you're always adding in 1. So if you just had 11 ones, then that would definitely be a composite number, because the alternating digit sum would be 11, and 11 is divisible by 11. I should have made clear, by the way, sorry. The divisibility rule for 11 is that if the alternating digit sum is divisible by 11, and that includes 0, then the number is divisible by 11. So any number here which has 11 ones or 22 ones or whatever is going to be divisible by 11, and therefore is definitely going to be composite. Now there are other times in which this number can be composite. For example, this one is composite because when you take away 101 from it, it becomes 101,000, so it's divisible by 101. But I can't say for sure that numbers of that form are definitely composite in that way. But I can say about 11, right? Every time we have a multiple of 11 number of ones in the number, it's going to be composite. So we just need to think. So A10 has 11 ones in it, because A1 has 2 ones, and A2 has 3 ones, and A3 has 4 ones. A10 has 11 ones. So, okay, our K is 10 then. We have a case. When K is 10, we know that we're composite. So which one of these rules does K equals 10 obey? It's clearly not just anything greater than or equal to 2, because lots of these are not divisible by 11, as we just discussed. And it's probably not something as simple as this. It's not going to happen that often. It's to do with the 11 divides idea, I think, because they're going to come across every 11. So let's just check the first one. If K is 10, we get K 10 to the 11 there plus 1, which is that. 10 to the 11 has 11 zeros after it. So replace one of those with the 1. When you add 1, you get this. And now I just need to check, does 11 divide this? Well, again, we just do the alternating digit sum to check. So it's 1 minus 0 plus minus plus minus plus minus plus minus plus minus. So it ends up just being 1 minus 1, which is 0. And you can just say 11, I guess, divides that. And so this is the correct one, and I think that is going to be our case that works. And so I think we're good to go. Question 6, the product of a number of odd integers is of the form 4n plus 1. So we can just take an example here, right, I guess. 17 is of the form 4n plus 1. But 17 is, I guess you could say it's 1 times 1 times 17. That's the product of an odd number of odd integers, if I'm not mistaken. But it's also 1 times 1 times 1 times 17. So is it necessarily any of these things? Is it an even number of those odds must be of the form 4n plus 1? Well, I guess that, well, here we've got 2 of the, here we've got 3 numbers of the form 4n plus 1, and here we've got 4 of them. So I don't think either of these two statements are true. Either this one or C, right? Because we have cases that are counterexample to both. And here we have none of these of the form 4n plus 3. So certainly we don't need an odd number of them either. So I think none of those statements are true, just based on writing down some examples of this thing happening. PQ equals SQ squared. It follows these things here. Again, probably using counterexamples is the best strategy here. So here's a case that works where P is not even, so that goes away. Just thinking of more trivial counterexamples, using 1 is good, because you always make some nice trivial things there. So S doesn't have to divide B, because of course 16 doesn't divide 4 here, so that goes away. Likewise, this one goes away for a very similar reason. Here Q squared is 16, which doesn't divide 4. So this one goes away as well, and we're just left with B. I mean, it's the only one that's left. You could come up with some good logical ideas as to why that's definitely true, using ideas of prime factors and having, when you have square numbers, it means your prime factors always come in even pairs. When you write a square number in prime factorized form, all the indices have to be even, and that leads you to be able to conclude this, I think, pretty easy. There are other ways to conclude it as well. But it's the only one that we don't have a counterexample for, so it must also be true. Here, of course, I was going to hammer in the log law, the Taylor Swift log law, which is what's right here. Log to base A of B is log to base Taylor Swift of B over log to base Taylor Swift of A. We can use that here quite nicely, right? Because we can replace log to base P of X with log to base X of X over log to base X of P. And then log to base X of X is obviously 1. And we can just now say that, therefore, moving the 1 over to the other side, that log to base X of P is 1 over alpha. That's also a useful thing to just know, that you can swap these two numbers and put a 1 over the top of the whatever constant equals. Useful thing to do. Of course, you do the same thing here and you say log to base X of Q is 1 over beta. You eventually get to. And that's good. Now we can start breaking down this thing. We can use the Taylor Swift log law for this one as well. Again, shoving in base X's in here. And by the way, you do not have to use the Taylor Swift log law for this. But if you are a true fan of the R2Juicy channel, you must use the Taylor Swift log law for this. I'm just saying, that's just the law. Anyway, log to base X of X is still 1. You can break this log law up like this, and then you can use these ideas that we got here, 1 over alpha and 1 over beta. And then, of course, you can combine them together and flip the thing over, and we end up with A as our answer to that question. Question 9, then. Now, question 9, you have to look at these coefficients here. And basically the rule is that if the coefficients are symmetrical, there is some kind of workable factorization you can use. That's just a rule of thumb. I'm going to say it's more than a rule of thumb. It's just a rule. If you see nice symmetrical coefficients, you've got to look out for some kind of factorization. Now, this one is not easy to spot. I was trying all kinds of factor theorem-y things by substituting in various things like 1 and minus 1 and NA and B and C and stuff, but nothing ever seemed to work. It's really tough to spot, but eventually you might be able to spot that you can break it into two quadratics that look like this. Because when you multiply there, you get AC, and then you get AC at the end as well, and then you can check yourself, but all of this turns out to be, you get all the squares nicely by doing all the expansions, and this turn out to be the same, of course, because of the symmetry within here as well. Not an easy spot to do at all, but the only thing that can keep you trying is knowing that if you see these nice symmetrical coefficients, there is some kind of factorization that will solve the problem for you. Of course, this solves the problem for us, because now what we're asking is, well, what do the roots of this look like, and what do the roots of this look like, in terms of whether they're complex or real. Of course, they're complex if b squared minus 4ac is less than 0, and real if it's above or equal to. But the thing is, because when you do b squared minus 4ac on each of these brackets, it ends up being the same thing, right? Because all that's happened is the c and the a have swapped. So if b squared minus 4ac here creates complex solutions, let's say, then it will definitely do it here as well, and you'll end up with 4 complex solutions. And likewise, on the other hand, if it makes positive, if b squared minus 4ac is greater than 0 and you make real roots, you'll make 2 real roots here, or 1 repeated one, it's the same thing, or 2 over here as well. So you're either having 4 complex or 4 real for this question. 10's kind of interesting. All you need to do really for 10 is write out the numbers in S and then write out the numbers in T. So substitute n equals 1 in, n equals 2, and n equals 3 in for each of these, and you make these 2 sets. Now, I couldn't be bothered to go much further than n equals 3 for this one, because the numbers get quite big quite quickly. But what we can immediately see is that for some reason, all these numbers in S seem to be multiples of 9, including 0, I guess. And all the numbers in T are obviously just multiples of 9. So, okay, is each number in S also in T? Well, possibly. If the idea of multiples of 9 here continues, then yeah, they are, because these are just the multiples of 9, and all these are eventually going to come up in the T set. Now, is each number in T also in S? Clearly not. Clearly, we're skipping multiples of 9. So we can immediately get rid of this, and we can also immediately get rid of C, because because C is just, the second half of C is just the one we already crossed out, B. So we're now down to A or D, and it's now, again, this is one of those times in TMUA where you're like, well, I don't have 10 minutes to prove this. Maybe you do if you're some kind of god, but you probably don't have 10 minutes to prove this. You should probably just go with your gut feeling, or just find a couple more if that would satiate you to think that, yeah, all of S is definitely multiple of 9, because like if the fourth one broke it, that would be annoying, right? So maybe just find a couple more. It turns out that, yeah, these things are always making multiples of 9. And the easiest way to do that is completely beyond the TMUA spec, but you can do a little bit of proof by induction. You can just say, well, I've already shown n equals 1 and 2 and stuff gives you multiples of 9, so let's just investigate n plus 1. If you haven't seen an induction, just ignore this step. Just ignore this. You'll see it eventually. You can write this like this, and then you can very intelligently write this like this, take away or add in this extra bit to make it all balance. And of course, this is a multiple of 9 because you've assumed proof by addition uses an assumption step. And the assumption is that this is a multiple of 9. And of course, you're just adding on another multiple of 9. So this totally works. And it's A. But again, you probably don't want to do that. And of course, in TMUA, you wouldn't have to do that because you don't need to do proof by induction ever in TMUA. In fact, you also don't want to prove things in general in TMUA because it's time consuming and you don't have that time to spare. So just go with your gut feeling. And whittle out every answer you can. A 50-50 guess is good in TMUA. Like, that's a good step to get to. Anyway, this person leaves, I appreciate the name. I'm not going to say it, but I do just know that I do appreciate the name at least. Leaves home at 8 a.m. to go to work. At 40 miles an hour, he's late by 3 minutes. So if we just get out some speed equal distance over time, if he goes 40 miles an hour, let's just call big D the distance to work, and big T the time that it would take for him to arrive perfectly on time. We have from the first sentence that if speed is 40, he travels the right distance, travels the correct time, plus 1 over 20, which is, of course, 3 minutes into an hour. So I've changed this to hours because this is in terms of hours. You actually don't need to do this because at the end you have to divide through anyway, so you would cancel any wrong units you were using. So you can actually just get away with putting a +3 here. But it feels more correct, at least, to do it in terms of hours. So I've done it like this. The next one looks like this because you're early by 3 minutes, so the time it took is 1/20th less than the correct amount of time in hours to do it. And then, of course, you just have to solve this for D and T. So do some cross multiplying, and then you've just got a simultaneous equation. You can just do this, take away this to get rid of the D's, and T ends up being a quarter, which means, of course, you can sub in and you get D is 12. And then, of course, you can just say the correct speed is when you do 12 over a quarter, which is 48, and you end up with the answer of 48 here, which will be correct. X heart y is the modulus of x minus y. Which of these statements is not true? Yeah, I don't really have too much to say about this question, other than you've just got to look for the one that's obviously not true. You can define, by the way, x minus y modded to be the distance between x and y. Like, so 5 minus 3 modded is the distance between 5 and 3, which is 2. And minus 5 minus -3 modded is just the distance between -5 and -3, which is still 2. That's why you always have a positive number, because we're now defining it to be distance. It kind of obviously makes C the incorrect one, because the distance between x and 0 is not always x, right? Because the distance between -6 and 0 is 6, not -6. So we can kind of just see that C is the wrong one just by coming up with a counterexample. That just, yeah. So I don't know. I probably said too much there. Just find a counterexample to the one that's kind of obviously wrong. Got tiles 1 to 100. So, okay, we have 100 tiles. When you do your first pass, there are 10 squares between 1 and 100. So you remove 10 squares. You remove every square number. So you remove 10 of them because there are 10 squares contained within the set 1 to 100. Now you've only got 90 tiles, and there are only 9 squares in there because, of course, you don't have the 10th square anymore. So you remove 9 tiles, which takes you down to 81. And there are still 9 squares in there because 81 is, of course, 9 squared. So you remove 9 squares and you get down to 72. Now there are 8 squares in there, so you remove 8, which takes you down to 64. And you might see a pattern here. We seem to just conveniently being ended up on a square number every time. And so when you take away another 8 from here, you get to 56, and that's after the 5th pass. And at this point, you could just count. You could say, well, these always seem to be coming in pairs, and then there's this one odd one up here. So you've kind of got 9 pairs of squares, and then plus the 10th, which gives you 19 in total. Or you could, if you wanted to be super careful about it, if you've got some spare time, you could count them super carefully all the way basically into the end where you can start doing your head. But either way, I think 19 passes is what it will take to do that. Very similar, this question, to something we saw in paper 1 of these guys' paper, floor function with a power. So, well, okay, I've marked on the critical points up to 2.5. Between 0 and 1, we're doing 2 to the power 0, which is just 1. And between 1 and 2, we're doing 2 to the power 1, which is just 2 every single time. And between 2 and 2.5, we're doing 2 to the power 2, which is 4 every single time. And that only lasts for half the distance of the previous one. We can add these areas up, right? It's 1 times 1, so that's area 1, plus 1 times 2, so that's area 2, and that's a half times 4, which is area 2. And so this is going to be total area of 5. And then we can now say on the other side, between 0 and minus 0.5, well, when you put in something between 0 and minus 0.5 into here, you're going to floor that down to minus 1, and 2 to the minus 1 is a half. So you're up at a half here. And then, of course, you can do a half times a half, which is a quarter, and add that on to 5, and we'll end up with our total answer of E. Basically, I should have said this at the start, don't integrate mod functions, or floor functions, or ceiling functions, or anything like that. Just draw them. It will be a definite integral. Just draw them and add up the areas by hand. That is just the way that you do that. 15 is added. It's a fun word, this, but it's added to a list of integers, and the mean is increased by 2. So basically, let's just say that there are n numbers. Their total is t, and the mean of the original set is m, which of course means that m is t over n. And now when we add 15 to the list of numbers, that means the total will go up by 15, the number of numbers will go up by 1, and the mean apparently goes up by 2. So we end up with this formula here. And now when 1 is added to the enlarged list, be careful to read this properly, 1 is now being added as a digit to the enlarged list. So we take this here, we add the total, we add in another 1 to the total, we add in another number to the total number of numbers, and the mean goes down by 1, which means the mean, which was m plus 2, goes down to m plus 1. And now this is a three-dimensional simultaneous equation, and we're being asked for how many integers were in the original list, so we're being asked for big N. So we just basically have to sit here and solve a three-dimensional simultaneous equation, which is basically never fun. I decided to just shove in this expression into m here, because I don't need little m. I'm looking for big N, right? So we've got these two equations now, and now I think I just cross-multiplied this. Okay, yeah, I combined these two things together to make that, then cross-multiplied to make this. And then some stuff cancels and you end up with that. And now you can shove this result for t into both of these slots here. And now you can start solving this for n, because it's not that hard to do. You've got a bunch of expanding to do. Okay, here you can collect those things together and then cancel out enough n's over here, which is fun. And then you can cross-multiply, I guess, which gives you this. And then lots of stuff falls out, which is nice. And you end up with n is 4 as your final answer. Okay, when you put in an integer less than 9 into here, you end up with a smaller numerator than denominator, and that's never going to be a square of an integer. So we'll just not bother doing all of those, and we'll start at 10. When you put in 10, you get 10 over 10, which is 1, which is a square of an integer, so that's good. And then you get 11 over 9 and 12 over 8, and I just decided to write all those down, and then say that's a square of an integer. The next one I think is all the way over here, that's a square of an integer, so is this, and so there are 3 of them, I believe. Unless I've missed one, which is very likely. Because, the mean, median, mode, and range is all 8, and there are 8 integers. Cool. So the total, if the mean is 8, and there are 8 integers, the total is 64. You have 8 integers. If the mode and the median is 8, then that means, well, the median is in between these two, right? But I can't really make that 7 and 9, because then I don't have any 8s. Because they're in order, right? They're going to have to be in order for the median to work. So if you make the median 8 and not put 8 to the side, then the mode is never going to be 8. So I think those are going to have to both be 8s. And now the range is 8. So if you choose maybe this number to be x, this number has to be x plus 8. And now how do you make this number here as big as you possibly can? Well, you make every other number as small as you possibly can, right? Because they're limited to adding up to 64. So the smallest I can make these guys is both x, and the smallest I can make these guys, because they have to be 8 now, because they're going in order, have to be 8. And now we can just add up all these to make 64, and solve, and we'll end up with x is 14. Sorry, x is 6, which means the largest one, of course, is 14, and that will be done. Okay, so consider some statements then. For polygons, all angles being equal is not sufficient for the polygon to be regular. I believe that's true. We learn at school that the definition of a regular polygon is all equal angles and all equal side lengths. We learn that rule for a reason, right? We don't just learn that they're equal angles because of rectangles, which have all equal angles but are not regular. So that one's definitely true. It's not sufficient to say the thing is regular just by having equal angles. A polygon can be drawn with a circle around it which touches all its corners, and that's sufficient for it to say it's regular. Well, this counterexample here also counterexamples this one here, because this has 90 degrees here and here, which means we can draw a circle around it, because cyclic quadrilaterals have opposite angles adding to make 180. So we can draw a circle around this, but it's definitely not regular, and so therefore it's false to say that it's sufficient for the polygon to be regular. And finally, for n, where n can take any value between 1, 2, 3, and 4, there exists a hexagon with n lines of symmetry. Now, we can pretty easily draw a hexagon with one line of symmetry, assuming that this is just... Oh, sorry, this is two lines, right? Here and here. And then one line is not hard to get from there, it's just now here. 3 lines is doable. You think of a shape that has 3 lines of symmetry, equilateral triangle, and then you just try and modify it to make it into a hexagon, and you can do that by cutting off the corners. And you will end up with a hexagon that has 3 lines of symmetry still. Now, again, one of these times in TMUA, I sat here for a minute or two trying to think of a way to draw a hexagon with 4 lines of symmetry. One way you could do it is you could start with a shape that definitely has 4 lines of symmetry, like a square, and try and modify it, just like the triangle. Couldn't find a way of doing that. You could also just assume that the line symmetry basically have to look like this, and try and construct a 6-sided shape around those lines of symmetry. Couldn't do that either. You can tell me in the comments, because I haven't even bothered Googling this. I kind of came to the conclusion, maybe a polygon with n sides only has lines of symmetry that are factors of n. So for example, a 6-sided shape only has lines of symmetry of either 1, 2, or 3. And then 0 maybe is just kind of an exceptional case. Maybe that's a true fact. Tell me in the comments if it is. But for now, I'm just going to say that final statement is also false. And 1 is the only true one. Question 19, we're just going to bust out some counterexamples here, like we always do. If x is less than y, we're seeing inequalities here, so we're immediately thinking negatives in our counterexamples. If you just make x negative, then the inequality should flip, and so that's definitely not true. Here, again, if you just make x negative, then when you divide by negative, the inequality should flip, so that's definitely not true either. And down here, of course, if we skip to this one, if x is less than y, if we just here make if we make z negative again, it's going to flip it, and because they haven't restricted us on z here, have we? So therefore the answer is clearly C. C makes a lot of sense. When you add something into both sides, you don't mess with the inequality no matter what you're adding in, unless I guess you add in a complex number, because complex numbers don't really have size in that way. But it said they were real, so we don't have to think about that either. Question 20 is a really interesting question that I actually learned something from, which was nice. Absolutely could never be asked in a TMUA paper, because it gives an unfair advantage to those who actually know how to do integration by parts, or to those who just memorize that log x integrates to x log x minus x. But yeah, let's integrate this without parts. Really fun. So we're going to draw the log x graph between 1 and a half, and we're looking for this area, right? That's the area we're looking for. So we're agreed on that. It's a negative area, that's fine. That's the area we're looking for. What we can do, in fact, maybe I have questions now about this answer. Maybe I have questions, I'm not sure. Anyway, what we can do to integrate this is we can do something really sneaky and really fun, which is draw the line y equals x, that's the line y equals x, and say, let's just reflect that graph in the line y equals x, which looks like this. And then let's draw the applicable area in the same place, which is this. Now, if this is the graph y equals log of x, and we've reflected it in the line y equals x, we know what this graph is. It's the graph y equals e to the x, because inverse graphs are reflective in the line y equals x. I think I have a video about that on the channel somewhere. If I don't, someone else does on YouTube, who's better than me anyway, so just watch theirs. But inverse graphs are symmetrical in the line y equals x. So if this is the line y equals log x, this must be the graph y equals e to the x. And of course, we can just integrate e to the x without parts. So if this is the coordinate log of a half, which it is because we just substitute a half in to get log of a half down here, that means this x coordinate there is log of a half. And so we're just integrating e to the x between log of a half and 0. Except we're not really, because that would find us all of the area underneath this graph. We need to take away this rectangle, and this rectangle is log of a half wide and a half up, because this distance a half is the same, although it doesn't look like it on my picture, is the same as this distance a half. So we also need to take away a half into log of a half. Now, why am I adding that in? It's because I've animated this wrong. Initially, I took this away, but then I added in a vertical line to show that I'm plussing. And the reason I'm doing that is because log of a half is a negative number already, right? So if I take away a half times a negative number, I'm actually adding that in, which I don't want to do. So if I add it in, then I'll be taking away because this is still a negative number, which is what I want to do. And now, of course, e to the x just integrates e to the x. We can shove in the numbers and we can evaluate, and we end up with this here, I think. As there should be a minus in here somewhere. Why is that? Oh, sorry, because this is log to the 2 minus 1, which then puts the minus in front, and we end up with the answer C here. Except I'm kind of wondering whether that's correct now, because log of 2 is less than 1, right? So this is a positive number. But of course, when we integrate this between a half and 1, I didn't think of this when I was making the slides. Of course, the area is underneath the x-axis, so the area should be defined to be negative. So actually, I think the correct answer is log 2 minus 1 over 2, because, of course, when we're integrating, we're going to get a minus number out of it. And that's the flip we need to make when we're doing this fake integral, because, of course, that integral is a positive thing. So I think the answer should actually probably be log 2 minus 1 over 2. But correct me if I'm wrong. I'm just ad-libbing at the moment. Correct me if I'm wrong in the comments about that. But I think that's probably true. Anyway, lovely paper. Again, I'll say it like I said at the start. Beyond Horizon Tutors, description, link is in the description below. They do tutoring and they have more papers for purchase. So I would suggest you think about doing either one of those.